You can build a perfectly valid Bitcoin transaction with no internet connection. In airplane mode, in a bunker, on a laptop that hasn't been online in days, right? The transaction doesn't care. It's like writing a check at your kitchen table. The check is valid the moment you sign it. Mailing it to the bank is a separate step. And this video has 2 acts. Build the transaction, then broadcast it. A wallet builds a transaction in 3 steps. Follow Alice as she pays Bob for a podcast. Step 1, know your coins. Your Bitcoin wallet does not store a single number called balance. It maintains a list of UTXOs, unspent transaction outputs. Each UTXO is a discrete chunk of Bitcoin that hasn't been spent yet, an individual coin in a digital purse, some worth 0.05 Bitcoin, others 0.1. The balance displayed is just the wallet summing this up. 2 kinds of wallets exist. A full node stores every UTXO on the entire network and can verify any transaction. A lightweight client tracks only your own UTXOs. Efficient, but relies on the network for full verification. Step 2, select inputs. Alice needs to pay Bob 0.015 Bitcoin. Her wallet scans her UTXOs, picture a purse with separate coins inside. She holds 5 coins, including a large 0.1 and several smaller ones, 0.005, 0.008, 0.002, and 0.003. The wallet picks the simplest path. The 0.1 coin alone covers the payment. Select it, and done. Now consider an alternate scenario. Without that large coin, the wallet must combine smaller UTXOs. 0.008 plus 0.005 gives 0.013, then add 0.003 to get 0.016, just over the target of 0.015. 3 coins slide together to form the input side of the transaction. It's like reaching into a purse and pulling out coins one by one until you have enough on the counter. Step 3, create outputs. With the 0.1 Bitcoin UTXO as input, the wallet creates 2 outputs. Right? Output 1, 0.015 Bitcoin to Bob. Attached to this output is an output script, a small program that defines who can spend these funds. It essentially reads, this output is paid to whoever can present a signature from the key corresponding to Bob's public address. Only Bob's private key can produce that signature. Output 2, change back to Alice, 0.0845 Bitcoin. Think of it like paying with a dollar bill for a 70-cent item. You get change back. Now let's look at the math. The input is 0.1 Bitcoin. The outputs are 0.015 to Bob plus 0.0845 in change back to Alice, which together equals 0.0995. That leaves a gap of 0.0005 Bitcoin. Here's the key insight. The fee is never stated explicitly. There is no fee field anywhere in the transaction data. Instead, the fee is implied. It equals total inputs minus total outputs, right? Whatever amount is left over after the outputs, the miners collect as their fee. Alice's transaction is complete, signed, sealed, ready. But it still sits on her device, time to broadcast. Remember the check analogy? The check was valid when signed. Delivering it was a separate act entirely. This transaction is self-contained. It carries everything any node on the network needs to verify it independently. That means Alice can transmit it through any channel, Wi-Fi, mobile data, a wired Ethernet connection, or she can paste the raw transaction hex into a Block Explorer website that relays it on her behalf. She doesn't need to connect to Bob's wallet. Bob doesn't need to be online. The Bitcoin network is transport-agnostic. The transaction is identical regardless of how it arrives. Once the transaction reaches any single node on the Bitcoin network, the gossip protocol takes over. Gossiping is a propagation method where each node tells every peer about new information, like a rumor spreading through a crowd. The network has no central relay. Each full node connects to several peers, typically 8 or more. When a node receives a valid transaction it hasn't seen before, it forwards that transaction to all its peers. Those peers validate it and forward it to all their peers. The cascade ripples outward from Alice's entry point. Within 2 to 4 seconds, the transaction saturates the entire network. Thousands of nodes worldwide, each holding an identical copy. On the receiving end, Bob's wallet watches for transactions containing outputs redeemable by his keys. Whether Bob sits 1 hop or 5 hops from Alice's entry node, the transaction reaches him in seconds. His wallet runs 3 checks. The transaction contains an output spendable by his keys. Check. The transaction structure is valid. Check. If Bob runs a full node, he also confirms Alice's inputs reference real, unspent, UTXOs. Check. Payment detected. Every node on the network now holds a copy of Alice's transaction. Step back and notice the division of labor. Alice's wallet is the accountant. It picked the right coins, wrote the output scripts, calculated the change. The network is a postal service. It doesn't care what's in the envelope, only that the envelope reaches everyone. Every node along the way is an auditor, independently checking that the math adds up before passing the transaction forward. No central authority constructed, wrote it, or validated this transaction. The wallet built it locally. Any communication channel could transmit it. Every node verified it independently. Construction, transmission, verification. Each piece fully decentralized. That's the Bitcoin design philosophy in action, but the transaction still isn't final. Right now, it floats in a pool of unconfirmed transactions called the mempool. How miners choose which transactions to include in a block and what makes a block irreversible, that's the next video.